talk about drawing structures. Mainly I want to complain and rant about how, what? All right, sometimes you see this going on. So I went to the store last night. Be hungry? Got a marshmallow. Got my marshmallow. See, I got one thing going in there like that, another one like that. All right, then you're telling me that the wedge coming out of the board like that, dash line is going behind the board like that. Look what I made, flat planer. 90-degree bond angle here, 180-degree here. This reminds me. Great xenon tetrafluoride. It has and we would call this thing, we call it square planar. All right, so you want to avoid doing this. Now the way you avoid doing that is you say 109.5, that's the perfect tetrahedral bond angle. Well, it approximates 90 degrees. So now I've gone to great lengths to draw these roughly at 92 or at 90 degrees. And then I say this one's coming out. Well, there's two in the plane of the board, one coming out, one going back. Put these two in the plane, one coming out, one coming back. Well, 90 degrees is okay. All right, these look a little wider than 90. These are probably 109.5. So what I try is keep these the same versus if I have my wedge on the right, I'm gonna put my wedge on the right, dash there. And that typically works. You wanna avoid this. Other bad things, question. Draw and name each internal alkyne with the molecular C5H8. So I would probably do it as well, or maybe not the first part, maybe the first part. A lot of people didn't even read the word internal. I mean, make that look like it. And that really simplified things up, but I think people just do something like this. 1, 2, 3, 4, 5, 6. You might say, okay, I'll put the triple bond there. 6, I'll put the triple bond there. And then there really wasn't a whole lot of options. Got it. 6. All right, these are all really bad. So I brought in an internal alkyne, triple bond. You can always tell hybridization by shape. This carbon and this carbon have a bond angle of 180. What does that tell you? sp hybridized, sp hybridized. The way you really want to write is to say, okay, there's one carbon, 2 carbons, there's my 3rd carbon, 4th carbon, 5th carbon, 4th, 6th. All right, now I'm like, okay, it's this thing, and this was 2 hexyne, 3 hexyne, and this was 4 methyl 2 pentine, excuse me, 4 methyl 2 time. All right. So on this, what we don't want to forget is valence shell electron pair pulse group of electrons and that far apart predicts shape. So maybe we need a little nomenclature review. Constitutional ice, draw and name C6H4 ice. Or maybe, all right, yeah, let's just go ahead and do that. So I start off with straight chain, cut a carbon off on number 2 carbon, put it on 3, and then I about goofed up. What other crazy do? Are there any other possibility? I think that exhausts it now. So fully saturated 6 carbons gives me 1, 2, 4, 5 compounds. Let's make it simpler. Just draw each isomer of a saturated alkane, 5 carbon chain, pentane, chop off a carbon, put it over here and figure I got the same, put it there. Methyl. Now I'm gonna chop off this carbon, put it here and realize I got the same compound. Now I have dimethylpro. So this only has 1, 2, 3. Now, how many of you believe less is sometimes you're all minimalist, get rid of all your finite problems, move into a small van down by the river? That's what I tell my wife. So what might be our, probably have to race, you know, I might start out 5. And the last thing we study is alcohol. And say, does this have the right unsaturation? So 5 twice plus 2 is 12. Here I got 8. That's a different 4. 4 divided by 2. I have 2 elements in saturation. I got my 2 pi. This ought to have a hydrogen 1, 4, 5, 7, 8. I can move it over there, and that's just the same thing. So I think I'm gonna better go back to the terminal. 1, 2, 4, 5. All right, now we're gonna have methyl. Now this might be all the alkynes we could have, right? What other crazy things could we have? We could have these dienes. All right, and then we could have a couple, right? What am I up to? 1, 2, 3, 4, 5, 6. I think I'm gonna have to save room. All right, so this, I've done all the double bond process. Well, probably not. 4 carb, 5. All right, then how am I gonna name? How about 2 methyl? I might as well. The double bond over there, we have I need 2 double. Have I exhausted every diene possibility? Well, I can have that. 1 double bond and a ring. Some of these I'm thinking, do I really want to name these? 1 methyl. How should I name this? Yes, sir. Thank you. Methylene cyclobutane. What about this thing? 1, 2, ethyl cyclopro. And I can probably move that double bond all over. Or stick. All right, and then I can probably the double count. How many structures in my up? Count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15. What do you think? Oh! Oh, look. With the double bond on on this thing, look, I could do that. Spiro. 1, 2, 4, 5. Yep, 2 degrees of unsaturation. So I always find that at 26 ice, it only has 3. Let's go to my favorite site to go to. Not 1, 15, 20, 21, 22, 24, 25, 26, 27, 28, 29, 30, 31, 2 on. Well, look, we have some R and S ice. Probably have an E and Z of these. Is that how they got? Gemini on Google told me there were 20. There are 36 possible structural isocyanides, and some of those have to stereo. Here's one we didn't get. 2, 4, 5. Oh, added carbon. All right, tomorrow we'll have a more formal review. Was this a review of naming? Maybe a review of stereochemistry drawing. Anybody hungry? Why'd the Girl Scout put Hershey's chocolate bars and marshmallows under her pillow?
So she wanted some more.
She wanted to sleep some more.